So what would have happened is in my main, so if you look at, I'm going to draw the stack now, okay, right, I'm going to draw the stack here. So I have a local variable called answer underscore rec, which is sitting in main. Okay, this is supposed to get the answer for the factorial of 6, which is 720. Eventually, we want this to have the value of 720 in there, right? And this is where my EBP is pointing in main. My ESP might be pointing somewhere here. I don't know. It depends, right? And why is this? Because of, let's look at it, sub ESP comma 12. You see this, right? You are doing that subtraction, and therefore ESP is pointing somewhere slightly above. That's a local variable space that has been allocated. So you'll have answer underscore rec here, which is in EBP. So if you look at it, answer underscore rec is in EBP minus 8. The local variable n is in EBP minus 4. Okay, so maybe I'll make that accurate. This is n. This is answer underscore loop, and this is answer underscore rec. Okay, EBP minus 4, EBP minus 8. No, it's the other way. This is recursion and this is loop. Okay, perfect. So this is where ESP is, and what you are doing now is you have loaded n with 6, you have moved that into EAX, and you are pushing EAX onto stack and then calling. So what would have happened? So this has got initialized to n equal to 6 in main, because I have said int n equal to 6. So when this statement executes, right, that move divert pointer n EBP minus 4 comma 6 would have happened, and it would have got initialized to 6. Now what you are doing, you are going to cause a push EAX and then call fact. Okay, so this EAX has the value 6. So you have pushed 6 onto stack, okay, and then you have called fact function. Now after you do this fact, what will you have? You will have in main add ESP comma 4, because you have done your this thing. So after fact you will do add ESP comma 4, right? So this return address is what will get pushed onto stack. Okay, and this is first pushing, then when the call happens, okay, you will have the return address being pushed onto stack, right, and then you will go into that function fact. Okay, now it's interesting to note that this fact function has one push ECX, but the prologue does not have a sub ESP comma something. Okay, this is very, very important to note. Okay, so that is sort of very critical, and it is important to understand why that statement was used there. Okay, so if you look at this function fact, it has only one local variable. So instead of doing sub ESP comma 4, right, you can as well achieve that by just doing one push. Okay, by pushing one 32-bit, what will you do? You will actually move the ESP up here. So the ECX may have some junk value, okay, and this is the ECX value that is happening because this prologue is push EBP, sorry, so you will first push EBP onto stack. So the EBP main, right, will get onto stack. So this is EBP main, right, then normally I would have done subtract, move EBP comma ESP. Okay, so actually, so you are now moving EBP, so the EBP will be made to point here after this. Okay, after this statement, so push EBP, move EBP comma ESP, right? And then you are doing push ECX onto stack. So what are you doing now? You are pushing one more and moving ESP to this point. So this is ECX, which could have some junk value, it doesn't matter. But what this statement is doing is it is allocating the local variable space for ANS. That is all it is doing. Okay. So now what you have actually done is you have gone into that, you have gone into the function, you have allocated local variable space, and then you are executing some instructions to check if the num is 0, but that is very similar to what we did in the loop function also. You check if for I equal to 1, I less than or equal to n. So those statements are very similar. Okay, so there is no difference in that aspect. However, after you do this, what do? You evaluate num minus 1. Okay, where is num? This is your num. This is the function parameter num. So you evaluate num minus 1 and that becomes 5. Then you push 5 onto stack. Okay, this is your num minus 1. And then what do? Your ESP has again moved here. Right? Now, when you actually come out of the function fact for the value 6, the answer 720 should be sitting in this local variable space. Where is that? This is where 720 should be. The 6 factorial answer should eventually go there. Okay, but in order to do that, we need to do so many other things. What is that? You have to now call this function fn minus 1 with fact of n minus 1 again. So that's why you have pushed that onto stack. Then again you call the same function fact, and when you enter that, you will execute these instructions again. You will push the value of EBP, right? This is the EBP fact 1, the first call. So you will push EBP, you will push, and then you will push the return address, right? This is the return address fact 1, right? And then after the call, you enter the function again and you will push EBP fact 1 like this. Okay, so your ESP is obviously going to move again like this with every push and all that. Then your EBP will be moved to this point, EBP fact 2. The second iteration of the same factorial function is now being executed. Okay, and then you enter here. What do you do? Again you will do push ECX. Okay, some junk value will be there in that. You will allocate local variable space here. So this is the answer of the second iteration. This is answer of the first iteration, right? So like that it has. Now, even now we have not been able to evaluate any factorial yet. Okay, so all we have done is we are now going to take the num minus 1 and evaluate it, decrement it by 1, and we will push that onto stack here 4. Like this, you will again do this call again. You will make a call to that function again. That means you will push 4 onto stack. Then you will again push the return address of the second iteration. Then you will push the EBP of fact 2 on on stack again. So what will happen is this stack will actually grow significantly, okay, for just a simple factorial function like this. And every time you call a function, remember, you have to execute the prologue and the epilogue. Okay, so you will push 4, then you will push 3, then you will push 2. Finally, when you come to 1, right, or when you come to 0, remember, you will find, okay, all I have to do is return 1 as my answer. So the local variable of that fact function will get the answer 1 there. Okay, and EAX will be loaded with that value 1 when you return back, when you return to the previous call of the fact function. Okay, and when you come there, the EAX value will be used in order to multiply by the num, and again that local variable will get that value. So after like 4 calls, you will get this to be what? You will get the local variable answer with the will have the answer of 5 factorial here. Okay, after 5 calls, finally when you come here, you will, after 6 calls, you will have the local variable here as 6 factorial answer. And finally when you come back to main, EAX will have the variable, will have the value 720 in it, and that will be loaded into the answer here, 720, right? So you can just imagine the amount of effort that you have put in to just do one simple calculation of num minus 1 into an answer, right? Now on the other hand, right, on the other hand, just look at the stack execution for the other program that we wrote. Int fact2 of int num, right, and int answer equal to 1 for I equal to 1, I less than or equal to num, I plus plus, right, and then we are saying answer is equal to answer into I minus 1, right. This is what we did in the loop, answer into I, answer into I, right. So you start with 1 and then you will get 2 factorial, 3 factorial, 4 factorial. So answer will just keep storing the factorial values incrementally, and eventually you will return. And then you do return answer, right, and then main, you're going to say int num equal to 6, right, answer loop equal to 1 or 0, I think we said 0, and then we said answer underscore loop equal to fact2 of num. Okay, now how will the stack look for this? Okay, so this is where, you know, I have my 3 variables for the main. Okay, this is n, I think we called it n there, right, n equal to 6, then we said answer underscore recursion, answer underscore loop. This is where EBP was pointing, ESP was pointing here, right, and what then we are going to call this function, which means you are going to push the n onto stack, n equal to 6 will be pushed onto stack. Then you will do the return address in main, right, and the fact2 function, right? Of course, this has local variables I, answer and all that, and therefore you have the local variable space allocation itself happening the traditional way. You are subtracting ESP comma 8 because you have two local variables. Okay, so what you do, you will push EBP of this. So this is my EBP main. So this will go on to stack. Okay, and then your EBP will be made to point out here, right, by through the move EBP comma ESP thing, right, because every push you have moved ESP like this, right, and therefore EBP main will be made to point here, EBP, right, and then you have subtracted ESP out by 8, and therefore this is where ESP will be. Okay, so EBP, I believe EBP minus 4 is the local variable I, and this is my local variable answer. Okay, this is all the stack that is needed in order to execute this loop function. The stack has been set up, and all you are doing is now going through some register calculations. You are checking if the answer is, you're checking if your I is less than n by moving it into some register, compare, and then you're loading it. So answer, you will start off with, you will start 1 factorial, then 2 factorial, like that you will go, and eventually you will get 6 factorial answer sitting here. That answer will be in EAX, and then when you come out of that EAX value will get loaded here, and you will get 720. Of course, the earlier function also did the same thing. We got 720 in both cases, right? Now, the key point is that the loop function, yes, it is also executing lot more instructions, but in effectively you can think of it as both the fundamental operation of evaluating n-1, num-1 and multiplying, all that remains the same across both these implementations. However, in recursion, in order to do that, n-1 and 1 multiplication, we are having to do all the prologue, epilogue, stack setup. So that's why that stack grows significantly. So remember that the moment you start accessing the memory, right, in terms of accessing the stack in terms of memory, your execution time will also start going up. Okay, so what is happening is effectively the the loop can be optimized very effectively, and if you actually optimize the compiler also a little more, you don't even have to go to these local variables back and forth again and again. You can simply do all the calculations with the registers, and once you are done, you just come out and give the value of answer to main, and then you are done with this whole thing. You don't have to complicate the whole process, and that is why it is a standard practice when you want real-time performance to take recursive functions and convert them to loops. Okay, so it's okay to write it recursively because the execution, the idea is easy to implement, but then for implementation and in order to get performance, it's a standard practice to compile these recursions into its equivalent loops, right? And therefore you will be able to extract maximum performance from the processor.